Friends, there was a time in the history of mankind when the entire world was discovered through navigation. Mostly all the Western countries they were very expert at navigation. So they used to start getting into the boats, and then they were always wondering about exactly how long the island is from the boat. So they wanted to calculate these distances. But these distances calculation used to be very laborious operation because the numbers involved were too big. So somebody created a magical formula for simplifying them. Just imagine, if I can convert multiplication into addition. That means instead of multiplying is always difficult than adding the numbers. Okay, dividing is always difficult than subtracting the numbers. Taking powers is always difficult than multiplication. So if I can find out some kind of a method, some kind of a mechanism which will convert the complexity of that particular operation one step down. For example, multiplication converted into what? Addition. Division converted into what? Subtraction. Powers converted into what? Multiplication. Now that kind of instrument is nothing but logarithm. So in order to understand the concept of logarithm, basically we have to understand the concept of indices. In mathematics, we always create certain short forms. For example, if I want to write 2 multiplied by 2 multiplied by 2 multiplied by 2, right? So mathematicians said that instead of writing 2 4 times, it will be easier if I indicate by writing what? 2 raised to 4. So this convention made it very clear that what is to be multiplied? 2. How many times it should be multiplied? 4 times. So 2 raised to 4 was a notation reserved for this. Now if I have 2 raised to 4 and then again I have here 2 raised to, this can be written as what? 2 raised to 3. 2 raised to 3. Now if I multiply both, that means 2 into 2 into 2 into 2, right? Multiplied by 2 into 2 into 2, right? So it is like multiplying 2 raised to 4 multiplied by 2 raised to 3. But this is nothing but how many times 2 has appeared here? Exactly 7 times. So 2 raised to 7. Correct? Now this notation, which was actually invented only for creating a short form and easier notation. But now if I translate this notation into the form of alphabets, so it is like, A raised to X is equal to Y, that kind of a thing, So for example, 2 raised to 4 is actually equal to 16, right? So 2 raised to 4 is equal to 16. From this kind of notation, the indices were invented. So this number X was called index. This number A was called base, right? And this is the power, xth power of A. This is written as xth power of A is Y. Or we say A raised to X is equal to Y. A raised to X is Y. So that is how this is called index, and therefore there are certain laws of indices. Now the laws of indices, now let us see what are the laws of indices. Let us take a review of all laws of indices. This chapter is not about indices, therefore I will be very brief about it. So let us talk about laws of indices. Laws of indices. What are the laws of indices? The very first law states that any number A raised to 0 is always equal to 1. The reason behind it is, I'll show you a little later. Okay. So A raised to 0 is 1. Okay. So second law says that a raised to m multiplied by a raised to n is nothing but a raised to m plus n. Just now we saw one illustration of this law only. Okay. Now third is a raised to m divided by a raised to n is a raised to what? M minus n. Correct? The fourth law is that if you take a raised to m and that is raised to n, that is same as a raised to n raised to this is same as a raised to n raised to m. That means they are interchangeable, and this is nothing but a raised to what? Nm. Okay. The next law is more about notation. So if you write the radical sign, if you use radical sign, say nth root of a. Nth root of a. So n, this is called a radical sign. This is a base. Now this is equal to what? A raised to 1 upon n. Correct? So that is the notation introduced here. So nth root of a is equal to a raised to n, 1 upon n. The next is, if a raised to m is equal to a raised to n, then what happens? Then either m is equal to n or a is 1. Now that is very funny. Most of the people do not understand this condition, because 1 is an exception to this law. 1 raised to 100 is 1 and 1 raised to 1000 is also 1. So you cannot conclude 100 is equal to 1000. 1 raised to 1000 and 1 raised to 100. Okay. Now both are 1, correct? But that doesn't mean 100 is equal to 1000. So therefore, using this law, you have to be a bit careful, because it is conditional statement. For a not equal to 1, you can always say that m is equal to n. Or you may say like this: a raised to m equal to a raised to n implies m is equal to n provided a is not equal to 1. So these are the fundamental laws of indices. I don't want to go into the nitty-gritties of how exactly these laws have evolved and all that. That is not a topic. But these laws are actually very useful for understanding what is logarithm. Because logarithm is a inverse process. What is a question that we are solving by using indices? We are asking ourselves, what is the second power of 3? When I say 3 square, 3 raised to 2, I am asking myself a question, what is the second power of 3? And my answer turns out to be what? 9. Okay. Then I ask myself a question, what is the minus 1 power of 3? Then it becomes what? Answer is 1 upon 3. So my interest is, I know the base, I know the power, and I want to find out this base raised to that power gives you what? So I know a, I know x. Now, one more condition I want to add here, that a is always taken as positive. Why a is positive? Because negative quantities will create trouble. If you take minus 1 raised to half or something, imaginary numbers will arise. So, in order to avoid that difficulty, a is always taken to be what? Positive. So, always remember, for all these laws to be true, a has to be greater than 0. Okay, so that is called base. So, when I say, I know a, I know x, that means I have to take xth power of a. Xth power of a is y. But sometimes my question will be inverted. That means I may ask you a question, which power of 2 is 8? Which power of 2 is 8? Look at this question. So there is a statement that 2 raised to 3 is equal to 8. So in this case, my question is, what is third power of 2? What is third power of 2? But the same, sometimes I may ask you a question, which power of 2 is 8? Which power of 2 is 8? Obviously, from this statement, it is 3. But This statement is exactly reverse of what? Here now we are not interested in finding the power. In fact, we know what is the power. We want to find out which power. That means I want to find this index. So here index is the target, and earlier the power itself was the target. Okay. So this same question can be written as like this. What is log of 8 to the base 2? What is the log of 8 to the base 2? Means I am asking you which power of 2 is 8. Which power of 2 is 8? This question and this question is absolutely same. Followed or not? So for example, if I am asking you what is log of 1000 to the base 10? That means I am asking you which power of 10 is 1000? Which power of 10 is 1000? You know it is 3. So the answer will be 3. So the same statement, whatever the information is contained here can also be written as 10 raised to 3 is equal to 1000. Correct? So 10 raised to 3 is equal to 1000. This statement and this statement, they are equivalent. You know, so this implies this and this implies this. Why? So we are not conveying any new information. We are just changing the notation. But changing notation is not the only thing. We are interested in a different thing here. Here 3 is an answer. So here 3 is an answer. Here 1000 is an answer. Question is what is 10 raised to 3? And here the question is which power of 10 is 1000. So we are reverting. In other words, a raised to x is equal to y. So I want to find out what is the power of a. Which power of a is y? Which power of a is y? Right? So that is what? So this is a exactly opposite or inverse operation of indices. Okay. So if I want to generalize this, then so for example, I will give some examples and get used to it. Suppose I write here log of 27 to the base 3. What am I asking you? I am asking you which power of 3 is 27. A little bit of calculation will tell you 3 square is 9, 3 cube is what? 27. So which power of 3 is 27? It is 3. Correct? Now if I want to remove this logarithmic notation and go to the normal notation, what I am saying is 3 raised to 3 is equal to 27. So these two statements are absolutely same, but their intention is different. Here I am trying to find out which power of 3 is 27. Here I want to find out what is the third power of 3. So these two questions are different, but they are exactly opposite of each other. Correct? So here a raised to x is equal to y. Suppose this is the statement. If I want to transform this same statement in logarithmic form, I will write log of y to the base a is equal to what? X. So the base for both notations is same. So log of y to the base a is equal to x. So log of y to the base x is equal. So in other words, if a raised to x is equal to y, then, and remember the condition on a is what? Greater than 0, then log of y to the base a is equal to what? X. The log is a short form of logarithm, right? So in other words, when I say log of y to the base a, I know that a raised to x is equal to y. If this statement is to be translated into logarithmic form, it simply means a raised to x is equal to y. Okay. So this a from here, it comes here, this x goes up and this y remains here, correct? So y, so you can clearly see this y remains here, this a goes here, right? And this x becomes the power. It's very simple. If I write log of 5 to the base 2 is equal to say x, then it means 5 is equal to 2 raised to x. Very simple. This is equal to this raised to x, right? So that is how this notation works. So you can always go back to and fro from this notation to that notation. So both the notations are available for us. Okay. So that gives me a complete definition of logarithm. So let us look at the definition of logarithm, right? So see. So it's like this. If a raised to x is equal to y, if a raised to x is equal to y, provided a is greater than 0, but a is not equal to 1. I already told you the dangers of taking a to be 1. Although it is positive, we are not allowed to take 1 there. Okay. So, because a raised, if it is taken 1, the 1 raised to 100 is also 1, 1 raised to 1000 is also 1. So, we will not get any unique answer for that. Okay. So, therefore, a raised to x is equal to y provided a is greater than 0 and provided a is not equal to 1. Then log of y to the base a is always equal to x. Log of y to the base x or a is always equal to x. That is the definition of logarithm. Okay. Okay. So this is how the logarithm. For example, if I ask you what is log of, let us say 1000 or 10,000. Okay. What is the log of 10,000 to the base 10? Which means which power of 10 is 10,000? So, fourth power of 10 is 10,000. The same statement, if I want to write in an index form, then this 10 will go up, 10 will go up, 4 will go even up, and the answer will be what? 10,000. Correct? So, these two statements, you should understand their equivalence. Okay? So, these two statements are almost same, right? This notation is logarithmic notation, and this notation is index. The purpose of two notations is to answer two different answers, to find different answers. Okay. So that is what the definition of a logarithm is. Okay. Now, so I will write the definition in the corner of this board like this. If a raised to x is equal to y, this implies log of y to the base a is always equal to x. Don't forget, provided a is greater than 0 and a not equal to 1. Correct? Now, once you get that, let us now go about understanding laws of logarithm. Now, since laws of logarithm itself is an inverse of exponential, it all depends, laws of logarithm come from the laws of indices only. Okay? How? We'll see. So, the first law, what is log of, for example, 1? Log of 1 to any base a. For all the notation, this is a blanket assumption. A is positive and a is not equal to 1. I don't have to specify it again and again every time. Correct? Provided a is positive and not equal to 1, then log of 1 to the base a is 0. Why? Because we know a raised to 0 is 1. Right? A raised to 0 is 1. So that is the first rule. Rule number 2. Rule number 2 is when the laws are log of m to the base a is equal to log of n to the base a. If that is the case, then m must be equal to what? N, provided the base is same. Okay? That is the second law. Now let us look at the third law. Third law is very, very easy. It says that log of m multiplied by n to the base a is equal to log of m to the base a plus log of n to the base a. As I promised, this particular law converts a multiplication to addition. So, difficult operation is converted into a simpler operation. That is the major triumph of logarithm. Today, nowadays, we have a lot of calculators and all that, so calculation is no more a problem. But thousands of years when calculators were not there, this was the only way of simplifying your calculations. Okay. The next law is log of division, that is m upon n to the base a, is actually what? Log of m to the base a minus log of n to the base a. Can you see that? A division is converted into subtraction, which is easier than division itself many times. Okay. So the next law is what? Next law is log of log of say log of, let us say, x raised to n to the base a. Log of x raised to n to the base a. Remember, I am putting a bracket around x raised to n. Why? Because taking nth power of x has to be done first. The bracket always indicates order of preference. So in this operation, there are two operations. One is taking nth power of x and the other is taking log. So which operation takes a priority? Taking nth power of x, right? That is why the bracket is here. If I do not mention this bracket, then you will be confused whether log is taken first or the power is taken first, right? So never write log of x raised to n. This is an ambiguous statement. Why? Because here it is not clear which is first. First you have taken log. If that is the case, then the priority will be here. If that is not the case, then priority will be here. So I will be very clear that log of x raised to n. So here nth power of x is taken first and then we have taken its log. Okay. So now according to this law, I told you that it will always take one step easier. So this means n times log of x to the base a. Correct? So this power comes down here, right, and becomes multiplication. Okay. So just imagine you want to find out something like 3.001 raised to 1000. Okay. Now, according to this law, it is just 1000 times log of 3.001. And how to find out log? Don't worry. There are tables which will allow you to find this, and then you'll multiply and you'll get it, right? So logarithm has made your job very easy. Okay. Now, so log of x raised to n is equal to what? N log x. Okay. Now, next rule is log of x to the base a raised to n. Now, I am taking the power of the base. What will I do? Here I multiplied, but here I am going to divide. So this means 1 upon n log of x to the base a. Can you see the simplifying power of logarithm, right? So log of, for example, if I say log of 27 to the base 3 cube, right? To the base 3 cube, this means nothing but 1 upon 3 log of 27 to the base 3. You can clearly see that the same thing, because log of 27 to the base 27 is 1, right? And this is also 1, right? And there's one more law I forgot. So I should write that as a zeroth log. And what is that? Log of 27 to the base 3 raised to 3 is equal to 1/3 log 27 3. So this is the log. Okay. Now, next law. But before I introduce the next law, I want to remove everything here because that's a very important law that I'm going to do. See, you have to understand one thing, that log of a to the same base a will always be equal to 1. Log of a to the base a is 1. Why? Because a is equal to a raised to 1. So a is equal to a raised to 1. So a raised to 1 is equal to a. Therefore, log of a to the base a is 1. So very clear. Which power of a is a? That is like asking you, right? So which power of a is a? 1. First power of a is a. Correct? So that's it. Okay. Now, remember one thing, that this is called a very important formula, that is called change of base formula. Change of base formula. So I have log of m to the base n. I have log of m to the base n, but I can change this base to any number I like, provided it is not equal to 1 and greater than 0. So right, that means log of m, I can change it to the base a divided by log of n to the base a, right? So instead of base n, I can change it to base a, but provided the law is this. So this is called change of base formula. One special case of this is very, very important, right? Log of m to the base n. So if I change the base to m itself, what will happen? So log of m to the base n can be written as log of m to the base m divided by log of n to the base n, to the base m, correct? According to this law, right? But log of m to the base m, as we have seen here, is always 1. So therefore, this becomes 1 upon log of n to the base m. So if you interchange these two things, if you interchange these two things, m comes here and n goes there, then you are taking reciprocal, okay? So log of m, so for example, log of, let us say, 27 to the base 3, right, is same as 1 upon log of 3 to the base 27, correct? So 1 upon log of 3 to the base 27. You can check. What is log of 27 to the base 3? Which power of 3 is, say, 27? 3. And which power of 27 is 3? It is 1/3. So 1 upon 1/3 it will become 1 upon 1/3. Therefore 3 is equal to 3. So these two things are same. Now the next law is very funny, because if I walk 2 units to the left and again 2 units to the right, where will I be? I'll be at the same place, because the two actions are reversed. If I go here 2 units and if I come back 2 units, I'll be same place where I was. So logarithm and exponential or indices are exactly opposite operation. So if you apply both of them on any number, you will get the same number back again. That is the statement that I'm going to write here. So what I'm saying is, if I say log of if I say log of a raised to x to the base a, I am first taking exponential of that number and then again taking log on that number. So I will get back the same number back again. So it is x. Why? You can see that one law tells you that x comes here. So this is actually what? X log of a to the base a, correct? Now log of a to the base a is 1. So therefore answer is 1. So log of a raised to x to the base a is nothing but what? X. Very, very important law. I am going to use it many, many times while solving the problems. So these are the laws of logarithm, okay? Now, if in case you are curious how these logs or how these laws have sprung up. So I'm not going to give you a detailed proof of all of them, but I'll just show you one proof that will give you indication of how these laws are created, okay? So just one or two, let's see. Suppose I want to make a statement log of m to the base n is log of m to the base a. Log of n to the base a is a very famous change of base formula. I'm changing the base from n to n to a. If you want to do that, this is what you have to do. So how will I prove this? So proof. Now proof is like this. So let us say let log of m to the base n, let us call it x, okay? Then log of m to the base a, let us call it y. Log of n to the base a, let us call it z, okay? So what I have to prove? So to prove that, what is log of m to the base n? X. I want to prove that x is equal to y upon z. This is exactly I'll prove. How? All I have to do is, I have to reverse this notation. So I know that log of m to the base n is x can be transformed into exponential notation like this. M is equal to what? N raised to x. This means m is equal to n raised to x. Statement number 1. Right? And then nextly log of n So m is equal to n raised to s. Then the log of m to the base a is y. This will imply what? M is equal to a raised to y. Statement number 2. Right? And next is log of n to the base a is z. Which means what? Which means n is equal to a raised to z. Statement number 3. Now combine all the 3 statements. In fact, value of m is written here. Value of n is written here. If I replace this m and n by replacing the values, what will I get? So what will I get? So putting 1, 2, 3 together, what do you get? You get like this. So this is the statement. M is equal to n raised to x. So what is the value of m? What is the value of m? M is n raised to x. Okay. So m is equal to what? What is m? M is n raised to x. Look at here. So m is equal to a raised to y and n is equal to a raised to z. So what is the relation between them? M is equal to a raised to y. So m is equal to a raised to y. A raised to y. That is m. And what is n? N is a raised to z. A raised to z. Now that is raised to what? That is raised to y. That is raised to x. Correct? So this is n. Right? So this n is a raised to z and it is raised to the power x. So from 1 I get this statement. This implies what? This implies that a raised to y is equal to a raised to zx, which means y is equal to zx because it is given a is not equal to 1. Correct? So therefore we have proved that x is equal to y by z. This is exactly what we were set out to prove. Okay? That's all. So we'll solve certain problems based on logarithms in the next lecture. Okay? थांबवून टाक. चल. किती झाले मग?